Welcome to this presentation. This session demonstrates an application of dynamic programming to address a classic system reliability problem. Specifically, the challenge involves allocating a limited budget to install parallel components with the objective of maximizing the system's overall performance. This case study is designed for undergraduate and graduate students who seek to deepen their understanding of dynamic programming's utility in solving complex resource allocation challenges. We invite you to explore this methodology with us. Let us now delve into the problem statement. We are to consider an electronic system comprising 4 distinct components. The successful operation of this entire system is inherently contingent upon all 4 of its components functioning correctly. It is important to note that the overall reliability of this system can be significantly improved by installing parallel units for each individual component. The critical data for this optimization task is presented in the table on your screen. This table illustrates the reliability, expressed as the probability of functioning, for each component. These values are provided for configurations involving 1, 2, or 3 parallel units per component. For instance, observing element 1 with 2 parallel units, we see a reliability value of 0.7. This indicates that if element 1 is configured with 2 parallel units, the probability of that specific element functioning correctly is 70%. We will utilize this data to determine the optimal allocation. Now we address the cost constraints and the optimization goal. The table provides the installation cost in dollars for 1, 2, or 3 parallel units for each component. In this table, the columns represent the individual components, from element 1 to element 4. The rows indicate the number of parallel units selected for each component, which can be 1, 2, or 3. We are limited by a maximum budget of $14 for this project. Our objective is to determine the optimal number of parallel units to install for each component using dynamic programming. This approach will ensure we maximize the overall system reliability without exceeding the specified budget. Before we proceed to the solution, let us clarify the fundamental concepts of system reliability for series and parallel configurations. First, we have the series system. In a series system, the entire system functions only if all individual components are operational. The overall reliability is the product of the individual component reliabilities. This is represented by a formula that states, the overall reliability R is equal to the product of Pi, for all components I from 1 to n. In other words, R is calculated by multiplying the reliability of component 1, by the reliability of component 2, and so on for all components. Next, we have the parallel system. A parallel system functions if at least one component is operational. In this case, the reliability is calculated as 1 minus the probability of all components failing. This is represented by a formula that states, the overall reliability R is equal to 1 minus the product of terms, where each term is 1 minus Pi, for all components I from 1 to n. Here, each term of 1 minus Pi represents the failure probability of each component. So, we multiply all the individual failure probabilities together, and then subtract that result from 1. Now, let's apply these concepts to our specific problem. Our system is composed of 4 components connected in series. Consequently, our objective is to maximize the product of the reliabilities of these 4 components. This brings us to our objective function. We want to maximize z, which is equal to p of x1, multiplied by p of x2, multiplied by p of x3, and finally multiplied by p of x4. In this function, the term p of xi represents the reliability of component I. This reliability is achieved by installing xi parallel units. So, x1, x2, x3, and x4 are the number of parallel units we decide to install for component 1, component 2, component 3, and component 4, respectively. These are our decision variables. To address our optimization challenge, we define the following core elements of dynamic programming, stage n. This represents each of the 4 distinct components in our system. State variable I. This is the amount of remaining budget we possess at the outset of each stage. Decision variable K. This refers to the number of parallel units selected for installation within the current component. Transition function. This function determines how the state changes. The new budget for the next stage is calculated by taking the current budget, I, and subtracting the cost of the current decision, which is represented as C sub n of k. Return function. The optimization is governed by the return function. It states that f sub n of I, which is the maximum reliability for stage n with budget I, is found by maximizing an expression over all possible decisions, k. The expression is calculated by multiplying two terms. The first term is the reliability of the current component, P sub n of k. This is multiplied by the second term, which is the optimal result from the previous stage, called f sub n minus 1. This function for the previous stage is evaluated using the remaining budget, which is the initial budget, I, minus the cost of the current decision, C sub n of k. In this stage, we initiate the system reliability optimization process, focusing solely on component 4. To simplify our calculations, and considering that one base unit has already been installed for each component, we now have a remaining budget of $4 that must be managed for purchasing additional units. Now, please refer to the results table at the bottom of the slide. This table specifies the best choice and outcome for each budget amount. If our budget is $0, we install no additional units, and the reliability remains at 0.5. If our budget is $1, we can install one additional unit, which increases the performance to 0.6. And if our budget is $2 or more, such as $3 or $4, the best option is to install 2 additional units, which brings the performance to 0.8. This is the highest result we can achieve for component 4. This table will serve as the basis for our calculations in the subsequent stages. Let's now proceed to the stage 2 calculation table. In this stage, we determine the best performance by evaluating the impact of installing 0, 1, or 2 additional units for component 3, depending on the available budget I. For a budget of I equals 0, we can only select 0 units for component 3, resulting in a total performance of 0.3. Similarly, for a budget of I equals 1, we are again limited to 0 units for component 3, which yields a total performance of 0.36. At a budget of I equals 2, we compare selecting 0 units, resulting in performance 0.48, versus 1 unit, resulting in performance 0.35. The maximum performance here is 0.48, achieved by choosing 0 units for component 3 and 2 units for component 4. As a detailed example, let's look at the calculations for a budget of I equals 3. If we select 0 units for component 3, it costs $0 and has a performance of 0.6. The remaining $3 for component 4 gives a best performance of 0.8, from the stage 1 table. The total performance is 0.6 times 0.8, which equals 0.48. If we select 1 unit for component 3, it costs $2 and has a performance of 0.7. The remaining $1 for component 4 gives a performance of 0.6. The total performance is 0.7 times 0.6, which equals 0.42. If we select 2 units for component 3, it costs $3 and has a performance of 0.8. The remaining $0 for component 4 gives a performance of 0.5. The total performance is 0.8 times 0.5, which equals 0.40. By comparing the results, 0.48, 0.42, and 0.40, we see the maximum performance is 0.48, achieved by choosing 0 units for component 3 and 2 units for component 4. Finally, for a budget of I equals 4, we assess all scenarios. We find performance values of 0.48 for 0 units, 0.56 for 1 unit, and 0.48 for 2 units. Thus, the optimal result is 0.56, achieved by selecting 1 unit for component 3 and 2 units for component 4. In this stage, we finalize the calculations for component 2. Similar to the previous stages, for each decision regarding component 2, the resulting gain is multiplied by the corresponding optimal value from the previous stage's table. Finally, the values in each row are compared, and the best choice is selected. For component 2, if no additional units are added, the probability of performance is 0.7. If 1 unit is added, the probability of performance in all situations is 0.8. And if 2 additional units of component 2 are added, the probability of performance will be 0.9. Next, we integrate the optimal performance probability from the previous table, based on the remaining budget. The optimal values obtained from these calculations are as follows. For a budget of $0, the only possible choice is 0 units, which leads to a final performance of 0.21. The optimal decisions for this budget are 0 units for component 2, 0 units for component 3, and 0 units for component 4. For a budget of $1, selecting 0 units also yields a final performance of 0.252. The optimal decisions here are 0 units for component 2, 0 units for component 3, and 1 unit for component 4. For a budget of $2, comparing the options, the maximum performance is 0.336. This is achieved by selecting 0 units for component 2, 0 units for component 3, and 2 units for component 4. For a budget of $3, after examining the choices, the best performance is 0.336. This results from a combination of 0 units for component 2, 0 units for component 3, and 2 units for component 4. And finally, for a budget of $4, after reviewing all possible scenarios, the best final performance is 0.392. This is achieved by selecting 0 units for component 2, 1 unit for component 3, and 2 units for component 4. In this fourth stage, we calculate the performance for component 1, assuming a total budget of $4. We analyze 3 scenarios based on the number of additional units. In the first scenario, we choose 0 units. The cost is $0, and the performance is 0.5. Multiplying 0.5 by the previous best performance for a budget of 4, which is 0.392, results in 0.196. In the second scenario, we choose 1 unit. The cost is $1, leaving a remaining budget of $3. The performance is 0.7. Multiplying 0.7 by the previous best performance for a budget of 3, which is 0.336, results in 0.2352. In the third scenario, we choose 2 units. The cost is $2, leaving a remaining budget of $2. The performance is 0.9. Multiplying 0.9 by the previous best performance for a budget of 2, which is 0.336, results in 0.3024. Comparing these 3 outcomes, we select the highest value, which is 0.3024. Consequently, the optimal decision for component 1 is to choose 2 units. Given this choice and the resulting remaining budget of $2, the optimal decisions for the components are as follows. Component 1 is 2, component 2 is 0, component 3 is 0, and component 4 is 2. Thank you for watching this presentation. If you found this tutorial on dynamic programming helpful, we invite you to explore our YouTube channel, Growing Science, for more educational content.